Welcome to this video on solving a system of equations by graphing. Let's begin. First, consider how many times can two lines intersect? In a minute, I'm going to ask you to pause this video and then see if you can attempt the following. First, try to draw two straight lines that cross exactly once. Then, draw two straight lines that never cross. Lastly, see if you can draw two straight lines that cross more than once. Then unpause this video and see if you are correct. Drawing two straight lines that cross exactly once is pretty straightforward. For example, this is a line, and this is a line, and as you can see, they cross exactly once. Most people can do that. Most people can also draw two straight lines that never intersect. For example, these two lines are parallel to the best that I can draw them by hand, and therefore they never meet. Or if you want to be really fancy, mathematicians like to say that parallel lines meet at infinity, which is the same as saying never. So what about trying to draw two straight lines that intersect more than once? Did you have trouble with this? Did you try to draw a line that wasn't straight? Well, what we can do is we can kind of cheat. So there's one straight line. What if we had a second straight line that landed exactly precisely on top of it? In other words, two lines that are actually the exact same line. We're going to see that when we solve systems of equations. So again, you could kind of argue that we cheated because as you read those statements, you might be assuming that I wanted you to draw two different lines, two unique lines that cross more than once. So let's look at this and develop this idea of having exactly one solution, having zero solutions, in other words, the lines never meet, or two lines, again, that happen to be the same line, so they have infinite solutions. So the steps to solving a system of equations graphically are almost identical to the steps of graphing a line. First, I would recommend that you put both equations into slope-intercept form because, as you learned in previous sections, that's probably the easiest way to graph a line. If you prefer one of the other methods we learned, that's totally fine. Then you need to graph both lines and determine where, if at all, the lines meet. Then you're going to have one of three answers. If you have two parallel lines that you graphed, then your answer will be no solution. If you have two lines that actually end up being the exact same line, in other words, they're lying right on top of each other, then you find out that you have infinite solutions because, again, they have infinite number of points in common because they're the same line. If I said, how much do you have in common with yourself? You would say, everything, because I am me. Same thing with lines. Or the other option, of course, is that you could have 1 point, like we saw, and so your answer would just be wherever they meet the ordered pair. So let's look at this in terms of a chart. So let's first take the example of having exactly one solution. So as you can see, I have two equations here. I have the equation y equals x, and then I have the equation y equals negative x plus 2. So first, I'm going to graph the line y equals x. So to help you, if you can rewrite this as y equals 1x plus 0, that means that the y-intercept is 0, and the slope is 1, so we need to go up 1 over 1, up 1 over 1. Once we've done this, we can draw a straight line connecting all of these points. Notice that in the other two graphs, we have the exact same function, y equals x. So I'm just going to take a minute and draw this line on the other two graphs, just to save time later. Okay, so again, I've graphed the line y equals x on all three graphs. For exactly one solution, we also have this other equation, and this other equation says y equals negative x plus 2. So 2 is the y-intercept, so we're going to start at positive 2. The slope is negative 1, right? So if the slope is negative 1, remember we can rewrite that as negative 1 over 1. So that means from this point right here, we need to go down 1 over 1, down 1 over 1, and so on and so forth. And then once we have enough points, then we connect them in a straight line like so. So hopefully you can see visually from this graph that this system of equations, these two equations have one solution. They meet exactly one time, and pause the video and see if you can figure out where that point is. If you said that it was the ordered pair 1, 1, then you are correct. So that is an example of a system of equations or two equations that have a single solution. Let's look at a system of equations that have no solution. So again, I've already graphed that first function, y equals x. Now I'm going to take a minute and graph the second function, which is y equals x plus 2. So the y-intercept is 2, so we start at 2. The slope is 1. Remember, we can rewrite 1 as 1 over 1. So we go up 1 over 1, up 1 over 1. Or, of course, we can also go down 1, left 1. So we have a bunch of points, and we want to connect them all together in a straight line. And hopefully you can see by doing this, I probably should have drawn arrows on my other graph as well, but you can see that they are parallel. So I want to make an important note here. Sometimes students graph lines that are parallel, and they look something like this. Okay, those don't look parallel to me. You need to, try your best attempt to make lines look parallel on your graph, make it visually obvious that they are never going to touch. Not that they are probably going to touch, just right off the edge of the paper. Okay, so remember, if these never meet, right, there is no point on the Cartesian plane. There's nowhere that they cross, so we literally just write no solution after we have demonstrated graphically the fact that they are parallel. Okay, so lastly, let's see what happens if we have two equations who have infinite points in common. So of course, we've already graphed the line y equals x. So look at this equation. We have 3x minus 3y equals 0. Now, we have a little bit of a pickle here because 3x minus 3y isn't in slope-intercept form. So I can do a few things. If I wanted to, I could try to make a table of values, maybe try to find the x or y intercepts. What I'm going to do personally is I am going to put it into slope-intercept form. So the equation is 3x, let me just check, 3x minus 3y equals 0. So I'm going to take a minute to convert it to an equation that looks like y equals mx plus b. And I've done this in previous videos, so I'm not going to spend a lot of time on the instructional aspect of this. If you don't remember how to do this, then please take a minute to watch that other video that I made. So we have negative 3y equals negative 3x. Now I'm going to divide both sides by negative 3, and we end up with the equation y equals x. Now what's interesting about the equation y equals x is, if we go back, we realize, oh no, y equals x is actually identical to the first equation we were given. Well, they had to make it look different, right? Otherwise, we would have seen right away that we had two of the same equation. So that's how they get away with being a little bit tricky. So if you want to, you could imagine graphing this green line directly over the red line. But for me, the way I think about it is, just graph one line. Why trace over it twice? It's kind of a waste of time. But what you definitely need to write, because this is incomplete, even though we've graphed everything, we need to write our final answer. So how many points does the red line and the green line, how many points do they have in common? Well, they have all points in common. They're the same line. So since they have an infinite number of points in common, we say that there are infinite solutions. Okay? So this is a really, really good infographic here if you wanted to write this down in your notes. You're going to end up with one of three cases. You're going to either end up with exactly one solution, where your final answer is some ordered pair. Of course, it's probably not going to be 1, 1, right? It's going to be some pair of numbers. If you have two parallel lines, then your final answer is going to be no solution. Or possibly you might be given two equations that when you do a little bit of work, you realize, oh, these are actually the same equation. The other one was just wearing a disguise, right? When you rip off that disguise by putting it into slope-intercept form, you realize, oh, it's the same equation. And so since you really are only given one equation and not two, you realize, oh, there's infinite solutions because a line contains an infinite number of points. So let's do some more examples and get some practice on this. So let's start with number 1. So we are given two equations. So again, I invite you to remember the steps in solving a system of equations. First, we need to put them both in slope-intercept form. Again, if you have method of graphing that you prefer over using slope-intercept form, you're welcome to do that. To me, that is the fastest way to graph it, so that's what I always do. As you can see, these are already in slope-intercept or y equals mx plus b form, so we don't really need to do that. We can go ahead and just start to graph both lines. So I will regard the first one, I will make that color that red. So the y-intercept, as you can see, is 3, and the slope is negative 1/2. So we go down 1 over 2, down 1 over 2, and so on and so forth. Notice I am making a lot of points. I am not just settling for 2 or 3 points. And the reason is you can sort of encounter this thing called drift. In other words, if I only plot 2 or 3 lines and I try to connect my points, what can happen is that I start out on the same line and then I kind of drift away. Now, of course, if you draw 2 points that are very far apart, that might not happen. But if your lines are very close together, that definitely can happen. Another practice that's a really good thing to get into the habit of doing is to label your lines. So that is the equation y equals negative 1/2 x plus 3. So then I will switch to, let's switch to purple. So we have y equals 3/4 x minus 2. So our y-intercept is negative 2. And then our slope is positive 3 over 4. So I'm going to go from there up 3 over 4, up 3 over 4, and so on. I could also, of course, go down 3 and left 4. So I have captured successfully the point at which these 2 lines meet. Hopefully you can see that that's right here. And it looks like we get to this point by going over 4 units and by going up 1 unit. So we have exactly one solution, and our solution happens or occurs at the point 4, 1. For the rest of the examples, I really want to encourage you to look at the set of equations, pause the video, try this yourself, and then unpause the video and see if you can do it all on your own. The more practice you can get on your own, the better off you are. So let's keep going. Now we have y equals 3/2 x minus 4 and y equals 3/2 x plus 1. So I'll use green for the first one. As you can see, the y-intercept is negative 4, so that's down here. And so from there, we're going to go up 3 over 2, up 3 over 2, up 3 over 2. Then I'm going to take a minute and draw a line to connect all of these points. Okay, and then I have the equation y equals 3/2 x plus 1. So I'll use pink for this. So we have 3/2 x plus 1, so we start at plus 1. From there we go up 3 over 2, up 3 over 2. We can also go down 3, left 2, down 3, left 2, down 3, left 2, and so on and so forth. Once you have enough points, something went wrong. Sorry about that. I think I didn't go over far enough. So down 3, left 2. There we go. Down 3, left 2. Okay. All right. So once we connect those points, looking at that, hopefully you can see that they are parallel. Remember, parallel lines never meet, or you can say that they meet at infinity, right? So does that mean that we have no solution, infinite solutions, or exactly one solution? If you said that it means we have no solution, then that is correct. Let's look at another example. Now, example number 3 is a little bit different. Remember our steps. The first step asks us to put both equations into slope-intercept form. For number 1 and number 2, we were lucky and they were already in slope-intercept form. However, in these equations, neither one of them are in slope-intercept form. They are, and this isn't something you have to know, but if you were curious, they're in what's called standard form, ax plus by equals c. So I'm going to go to the next page just so I have some more space to work, and I'm going to rearrange both equations so that they are in slope-intercept form. So let's start with the first equation. So remember, our goal is to have y all by itself on one side. That means I take everything that's near the y and I move it away from the y. So I'm going to start by subtracting 6x from both sides. So then I have negative 3y equals negative 6x minus 9. Then I have that negative 3 next to my x, and I need to get rid of it. So I'm going to divide everything by negative 3. So that gives me y equals positive 2x plus 3. So that's one equation. And again, if you forget how to do this, I made a whole video just on this activity of changing equations that are not in slope-intercept form into slope-intercept form, and I would encourage you to go and watch that if you've not already or if you forget how to do this. Okay, so let's do the other equation. So once again, we will draw a line through our equal sign. We will subtract 2x from both sides. Then we have 2y equals negative 2x minus 6. Then everything is going to get divided by 2, so we get y is equal to negative 1x, or negative x, minus 3. So these are our two equations. So what I'm going to do is I'm going to go back to the previous page with the graph, and I am going to write these equations in their new slope-intercept form so that they're easier to graph. So the first graph, we're not going to write 6x minus 3y equals negative 9 anymore. We're going to write 2x plus 3. So I'll call this equation 1 and equation 2. Okay, so the new form of equation 1 is forgot my y equals 2x plus 3. And then instead of 2x plus 2y equals negative 6, we have y equals negative 1x minus 3. Okay, so let's pick some colors and get to graphing. So I'll color the first one orange. So 2x plus 3, we're going to start at positive 3. Then we go up 2 over 1, and so on and so forth. We can also go down 2 and left 1, down 2 and left 1, till we run out of graph. Okay, then we can draw a straight line to connect all of those points. And then let's pick blue for the second one. So we start at negative 3. Okay, our slope is negative 1, so we go down 1 over 1, down 1 over 1, and so on and so forth. We can also go up and left. And hopefully, doing that, you realize exactly where that point of intersection is. Hopefully you guys can see that. It is right here. Okay, and if you're like, well, where is that point? Well, to get to it, we would need to go from the origin, we would need to go left 2 units and down 1 unit. So left 2 is negative 2, down 1 is negative 1. So this system of equations has exactly one solution at the point negative 2, negative 1. Let's do one more example. Here's number 4. So we have 2x minus 6y equals 12 and 3x minus 19y equals 18. So once again, just like in the previous problem, step 1 has not been done for us. So once again, I'm going to have an extra sheet of paper, and I am going to take a minute to rearrange these equations so that they are, in fact, in slope-intercept form. So I'm going to subtract 2x from both sides. I'm going to bring down my negative 6y, and then that's equal to negative 2x plus 12. I'm going to divide everything by negative 6, so that gives me y equals positive 1/3 x minus 2. So I'm going to do the same thing over here. I'm going to subtract 3x from both sides. That gives me a negative 9y equals negative 3x plus 18. Then I'm going to divide everything by negative 9. That gives me y equals positive 1/3 minus 2. What do you notice about these two equations? Well, after all that work, it turns out they're the exact same equation. So I don't need to write that twice. I'll just write it once on the previous page. So we have y equals 1/3 x minus 2. So let's color it red. So we'll start at negative 2, and then we go up 1 over 3, up 1 over 3, and so on and so forth. We can also go down, we can also go down 1 and left 3, like so, until we run out of graph. Okay, so we connect all those lines. Remember, I'll go back to the screen here, right? They're both the same. So, I mean, you could draw it once and then draw over it, but what's the point in that? But what you do need to do to communicate the idea that those two different equations, or the different looking equations, actually happen to be the same equation, is we need to say that there are infinite solutions. Okay, so if you don't mark that or write that on your paper somewhere, unfortunately you will not get full credit, like on a test or something. Okay, so make sure you, first of all, you would want to show all of this work. You would want to prove that they are the same equation when you put them in slope-intercept form. And then, graph the equation, because there's only one. And then lastly, make sure you indicate that there are infinite solutions, because again, there are two lines that actually end up being the same line. So hopefully at this point you are able to solve a system of equations graphically. So I just want to invite you to remember that these are the steps. First, put them in slope-intercept form. Then graph both lines, determine if they meet, and if so, where. And then remember, you're going to have one of three answers. You're going to either have two parallel lines, which means you have no solution. You're going to have two lines that actually happen to be the same line, so you would say that there are infinite solutions. Or you're going to have some ordered pair where the two lines meet. Okay, and those are the only three outcomes that you can have when you're solving a system of two linear equations.